So first, what is Hyperloop? Some of you may be familiar with this concept, but it's basically a high-speed electric train that is designed to run in a low-pressure environment, like especially like something similar to a vacuum. So SpaceX is running a competition that's been going on for the past, in its 4th year now, where college teams across the world design a prototype pod in order to run in these tubes and actually test at the SpaceX facilities in Hawthorne, California. So we competed last year. We got to the finals in LA and we competed. We ranked 13th, right?
Yeah.
13th out of the 20 that went there. And we are designing our new one for this semester, this year.
Yep.
Yeah.
And we just submitted our final design submission last week, roughly.
Yep.
Okay. So yeah, as Logan talked about, this is the just a shot from the actual final day of the SpaceX competition. It's a week-long process in which we got about 4 hours of sleep every night. It was awesome. That was a really fun experience. But basically what you do during this competition is you take your pod, you show your pod off to everybody, all the SpaceX engineers. You say, these are the different failure points. This is the different structural strengths of our pod. This is why we think it'll work in this way. And you have to basically go through a bunch of checks. I don't remember the exact number, but there was what was the size of that board?
There's about a few hundred line-long safety checklists that you have to get checked off for various different things on the pod that either SpaceX or Boring Company engineer has to make sure that your pod meets their requirements for safety.
Yeah, so basically you go through that process. Last year only 3 teams fully qualified to actually enter the tube, and basically what you find after we've gone there is it's all about how much of the safety stuff you can get checked off in the first day, because if you can get that far out, it takes so much longer to knock off the lower down the list stuff that it just getting through it as fast as possible is the biggest thing.
I mean, it's the same thing as when you guys show up to a competition, you want to get inspected on day one, you know, on that practice to get it all knocked out. That way you can go to that practice field and start practicing and then compete.
Yep. So this is a poorly cropped picture. Thank you, Vineet. I appreciate it. Of last year's pod. This was the guy in the middle is Michael Rao. He's our VCU president of the university. This is some of us from the competition that went out and made the journey to Hawthorne, California. Yeah, that was on the final day. I think that's most of it. The competition 3 pod was good, but we're looking to make large improvements to compete with this. This is Ward's Hyperloop pod from last year. It reached a top speed of 289 miles per hour. This is obviously a simulation, but we have the actual run in later. What was their budget on this pod, Matt?
I think over $700,000.
We spent $30,000. Yep. So I'll play that again. Okay, so this is this year's pod. We're not allowed to go into a ton of details about this year's competition pod because of NDAs, but basically that's the general layout of the pod. We have 4 MREX motors that are really high power going through a single speed transmission system that has a ball shifter, very similar to what you'll be using on this year's robot. The brakes, if Brendan wants to talk a little bit about just the generals of that. Maybe.
Yeah, so the braking system consists of 2 separate braking assemblies. You got one right here, one right there. They're pneumatically isolated, 2 separate air systems for redundancy. So if you lose one, you can still stop. And those are each one's actuated by 3 pneumatic pistons, and I'll go into a little bit more detail here in a minute.
Yeah. Can't really see the stability portions of it in here, so we'll get to that later.
Real quick, the whole
Yeah.
pod does ride on a I-beam,
Yes.
which is, it's not in this picture, but this is the bottom view of it, and this is the side profile of it, and the I-beam goes right through the middle of it. You probably saw the I-beam in Far's video that was just up there.
Yep. So yeah, basically we build the pod out of almost the exact same construction you guys use. It's a sheet metal construction for most of it, a lot of milled parts as well. We are targeting a top speed of about 290 miles per hour this year. We've developed some spring and rocker suspension assemblies for this year, and then you're using LiPo batteries and the other ones that I forget for the low pressure value.
Lithium iron phosphate.
Yeah, that one. You're using what control system again?
So we started actually looking into using the RoboRio that you guys are using on your robot, but unfortunately it was a little bit limited in what we wanted to do. So we're looking at different control systems from NI. One of them is called the Compact DAC. It's similar, and it's got just different modules that you can plug in to have all of your controls components communicate with one another.
If you've ever seen a 4-slot C Rio downstairs, it's closer to that. Something that we used to use instead of the RoboRio. Yeah. So when going about designing this pod, we developed, me and Brendan and a couple of other people developed a Mathematica profile to take an inputted mass that we expected the pod to be at, and the projected track length and stopping distance we wanted to stop in, and we auto-generated through this code the optimal gear ratios to use. This is the actual trajectory as it goes through the track. The one on the left is the position. So as you can see, this is the red line is the first stage of the gearbox transmission system. As we shift, we get into this blue region. That gets us to a higher speed, so we're using a low torque drive system initially to get up to speed fast, and then we go for a higher top speed by shifting. And then the yellow is our actual deceleration via the brakes. And that's the actual velocity graph. So you can see we get up to 120 meters per second, peak at the end, and then we go all the way down to 0 in a very short span of time. So this is the propulsion unit. We have 2 of these on the pod. We are using 2 MRAX 208 motors. They're really large motors. They put out roughly 460 Newton meters of torque total between all 4 of them. We will be using 10-inch aluminum wheels that we're custom lathing, and we have developed the polyurethane composite to put on there. Below it, you can see we have our vertical suspension system, and that plays a key role in applying a clamping force so that the pod itself is always constantly in contact and has the right kind of friction interacting with the I-beam. So, like I said earlier, we're using a 2-speed transmission system to get up to speed. That's an old version of our transmission system. It's been updated slightly since then, but it's using very similar concepts that you guys are learning in first. We're using a ball lock shifter, which is what you'll be using this year on your drivetrain, which is basically you have a hollow shaft with ball bearing balls, and you pneumatically engage those into the wheel to lock the wheel to rotate. And you're able to engage and disengage to switch the speeds. Just going through this pretty high level. Propulsion testing and validation. We have developed several MATLAB codes and Mathematica codes to test the forces and the shear stresses that we'd see or expect to see in this run with the on the actual polyurethane components. So I don't know if you guys have noticed this, but whenever you guys run a rubber wheel or a tread, you're actually gradually wearing it. So we've developed or designed our we've selected our polyurethane such that in this 15-second run, with all the torque that we're putting through these wheels, we're not going to burn out.
All right, so this is the braking. I'm going to go through kind of the iterations that we went through for this year. This is what we initially started out with. I believe each braking assembly weighed roughly 60 pounds. Went way overkill initially with the design. And then slowly as we iterated through, we refined the design inputs to, validation portion of it. Originally we were operating at 84 PSI gauge, and we had I believe they're 3 or 4 inch size bore pneumatic pistons on there. So it was pretty beefy. And this is a floating braking assembly, very similar to what's on your cars. And then we'll move on to the next slide. This is the final version of the braking system. We shaved 20 pounds off, so a third of the weight. We also realized that we only needed to be operating at 64 PSI gauge because we were using the reactionary force of the pistons. So when your physics teachers tell you to draw free body diagrams, it's very applicable to real life. It's very important. In this case, we found out we needed to be operating with less pressure, and the design inputs dropped down dramatically such that we could shave a lot of weight off the structure. You can see how it's clamping on the I-beam down here, and it's just riding on there. It's not disengaged up there. It's probably hard for you to see, but it just clamps down on the top of the I-beam. And then this is one of the analyses that we did on the structure itself. You can see all of the inputs on the forces. It's probably hard for you to read, but this the inputs for this were the same as on the last slide. And this is done in ANSYS, just analyzing the stress. Currently, we're refining this even further, and we're analyzing bolt pretensions. In this case, everything's bonded together, but what's running right now, in engineering building, is a simulation where you're modeling the bolts itself, getting pretensioned,
And applying force, yeah.
applying the force to clamp all of your material together. Right here, this is just a capped ISO view showing some stress concentrations. I believe this one was capped at 4,000 PSI. You can see the areas of stress concentration right here, right next to the cheesing holes, as expected. That's where your forces would be. So this was a good result, showing, okay, well, we're nowhere close to our yield strength of aluminum, which is about 37,000 PSI, when this is at 4,000 PSI. So that just validates that the structure itself for the braking system is good. And then we took it a step further, and we needed to analyze the thermal profile of the braking system. We just assumed that we're going to take all of the kinetic energy at max speed and convert it to heat, and then get a heat power with the braking time. And then we applied a lot of very conservative assumptions to just get our top temperature from friction on the brake pads. And you can see we're peaking at 300 degrees Fahrenheit on the brake pads, which isn't too bad considering what automobile brakes operate at. And in the next slide, we looked at how the heat is conducted onto the I-beam itself. And again, you can see it peaks at 250 degrees Celsius, so we're not going to be messing up the I-beam in any way.
So, stability. I mostly work on the horizontal stability. So, it is important because the I-beams are not perfect. There are segments of I-beam. You can't make an I-beam that's like
4,000 feet long.
4,000 feet long. So they break it up in segments about 10 feet per segment. So when they line them up, they're not perfect. So they have a max step of 1/4 of an inch on the side. Our team designed this to take an account of the step to stabilize the pod so that it won't shake too much, and to recenter the pod in the middle of the I-beam. And we use a spring and rocker system. So the spring is not taking on the direct shock. You have the rocker system. And we also are using polyurethane wheels, so that part is also taking a little bit of the shock in. This is one of our older designs. We've changed it up a little bit for space constraint, and we also found like a much better spring and damper system to work with it. And here is the vertical stability mechanism. Like Tyler said, it is a clamping mechanism. But there is also a step on the I-beam because they're not perfectly
Top to
matched.
bottom of the flange.
Yeah, so I think it's about
0.04 inches. So
0.04.
not a large step as it would be facing the I-beam like this, but it's still something that can induce vibrations and cause the pod to shake itself apart.
exactly. So you don't want that, and you want to have
That would be bad.
So you don't want that, and you just want to be able to take out anything so your pod wouldn't vibrate at such high speeds. So we also ran, sorry. But yeah, so these are just some of the specs that we use, like what kind of wheels, what kind of spring and damper that we're using. This is kind of like a blown up view of the CAD
itself.
Yeah, so I've changed from, instead of using a gas spring damper, we changed it to an actual damper. There was like a lot of research that went into it. Surprisingly, you can't really find a damper coefficient when you're looking for dampers, which is kind of dumb. So we did a lot of research. We were finally able to find a spring and damper that fits our needs and has the right numbers. So that's not the final design, but the actual one looks a lot better than this. And yeah, you got vertical, which I can't really. Basically the same thing. No spring and damper, just a spring though.
Yeah, because it's a lot less of a step, and we're actually using that spring. It's so when you go to cut sheet metal with they have these things called die cutters, which apply a shear force, and they just shear the metal. That's actually a die cutting spring, so it applies a lot of force, enough to cut through metal in the right application. Yep.
So we ran a ANSYS analysis on our original model to see where the highest stress is, to make sure the system is okay. And we found out that it's right on a thread. So we're like, it's fine, not a big deal, because it's all concentrated right there. We also did analysis, we made a MATLAB code on body displacement. So when you drive onto the step, your body, the whole pod is going to shift. So we're just looking at the body displacement and how fast it will go back to normal. So you can see the wheel displacement and the body displacement when it jumps, based on our math.
Okay. Basically what we've said. These are adapted slides from what we submitted to SpaceX in November, I want to say. So yeah. Okay. Matt.
All right, so on the power side, we obviously have these 4 really high power motors that we're going to have to power to drive the pod. So each motor is going to have its own battery system. This was done for redundancy, and also just the battery pack for each motor is going to have to be really huge, and parallelizing everything was going to be really complicated. So each one is running at about 470 volts DC with a potential output of about 180 amps, which is what we're expecting based on the torque we're trying to produce. So each of these battery packs is going to consist of 18 hobby-grade LiPo cells in series. The unfortunate thing that you need to take into account with these is, since you're running in a low-pressure environment, those types of batteries tend to swell when you're in vacuum, and batteries like that also swell when they're under a high load. So 2 of the considerations that we took into account to make sure that we don't have any issues with these batteries were, 1, to put them in a pressurized container. So we have a custom fabricated steel box that's going to be welded together, and then have a bolted on top cover with a gasket. And that's going to hold all of our batteries at 1 atmosphere of pressure. And then we're also going to constrain them within that box, so that even if we were to lose pressure in that enclosure, we'd still be able to maintain the restriction on the batteries, so that we wouldn't see any harmful things that could lead to thermal runaway, because these batteries are pretty dangerous to deal with. So that's how we're running the high power side. And then on the low power side, we have lithium iron phosphate batteries, which are incredibly safe batteries to work with. You can actually short the 2 ends together and not cause any issues to the battery. So you can basically run what would go to infinite current through the batteries with no lasting damage to them. They're also okay to be run in vacuum, so we have no real worries to deal with for that. And so these will be running all of the lower power, all the control stuff, all the kind of mission critical components for the flight.
And that operates at what voltage again?
Various different things.
Okay.
So for additional redundancy, we split up the packs. I think at this point we have 7 or 10 different packs based on however much we do for pneumatics. But each pneumatic system is going to be powered by its own set of batteries, so that if one set fails for any reason, we can still use the other set of brakes, we can still use the other transmission if we need to, and then all different sections of our controls layout are going to be powered by their own set of batteries. So it's just a high-level look of an older schematic for the high-power system. All the batteries are going to have their balance connectors, if you guys have used hobby cells before. It's basically just a way to monitor the cell voltage for each of them. They're each 6-cell batteries, and everything's connected up in series. And then we have a battery management system which actively balances the voltage on each cell to make sure that we're not sagging in any particular region of the pack. And then we have contactors throughout the pack so that when an actual user is plugging in the batteries, we're plugging in two 400 voltage, 200 volts, which is pretty dangerous. So we have contactors that actually do the final hookups of the batteries to make sure that a human isn't making those connections physically. And then our motor controller, which will output to the motors. Kind of went through all this of why we were selecting both of them. So the LiPo batteries can obviously output a super high current. Their power to weight ratio is really good. We looked into using the lithium iron phosphate batteries for our high power side, and also looked into 18650 cells, which are the same ones that are used in Teslas and a lot of electric cars. And unfortunately, the weight on those is just going to be too much and would cause a huge decrease in our speed if we use those. So we went with the LiPos because they're much lighter and
Efficient. Yep.
yeah, more efficient. The control system at a high level, we have, again, this is a little bit old, but we're planning to go with the compact DAC from NI to be able to communicate with everything. Our main computer is going to be an Udo x86 Plus to actually do all the processing and send out all the commands to everything. Again, power distribution is going to be those localized battery packs. Communications is something that is new this year. So last year, SpaceX basically gave you a wireless router. You had to hook up to it, and then they would control all the communication between your computer and the pod. This year, what's different is we actually have to design that whole communication system. They saw a lot of issues with it last year. There was a team that spent about 2 hours of loading their pod in the tube, closing the tube, lowering the pressure in the tube, and then they find out that they can't communicate with the pod. So SpaceX kind of saw an issue with that and then put it on us to try to figure out the best way to do it. So that's just a new challenge that we have to face this year. And then some of the sensors we're using IMUs, and inertial measurement units, to measure our angular and linear acceleration. We have displacement sensors to make sure that our stability is not thrown out of whack in any way, to make sure we're still centered on that pod, get a good state estimate. And then other things like pressure sensors, temperature sensors throughout the batteries, and motors and motor controllers to make sure everything's operating in normal ranges.
Mostly covered that, yeah.
Yeah, that's kind of what I just went through.
Yep.
This is an older diagram, just a really high-level view of our state machine to show you guys kind of what the pod goes through. So we start off with the pod off. We go through a system check to make sure all the different parts of the pod are have values in the ranges we're expecting. We turn our motors on, we arm them, and then we begin our acceleration phase. And then anywhere in here can end up going to a stop phase. But after our acceleration phase, during a normal run, we'd end up coasting for a little bit, make sure the motors are disengaged, and make sure we're ready to brake. And then we'd send the signal to apply the brakes. And then once the pod comes to a stop, analyze our position, see if we need to move the pod further towards the end of the tube at a low speed, or if we're stopped within our normal location and we can go in and retrieve the pod.
Yeah. And all of these decisions have to be made in about less than 15 seconds.
Yeah.
Yeah. So it's fast.
Mm-hmm.
Yeah. Yep. And this is just the world record run. This is the fastest any team or privately held company has ever gone in a Hyperloop vessel. This is that same pod I showed you earlier. And basically the goal that we want to get to. At the end of this, it reaches a max speed of 289 miles per hour, which is a lot. Yep. And that's basically the presentation. Hope we didn't go too in detail, but if you have any questions, happy to answer them.
How far did that go in that video?
That only went, I think, about halfway down the tube, so probably, I think, a little over half a mile.
But it was able to still reach 289 miles in less than half a mile. also insane.
What would be the goal as far as, like, it's going to be a people mover, correct?
Yeah, theoretically, the goal of the SpaceX competition is more to develop the propulsion testing and the brakes and the stability mechanisms for a future pod. The actual life support systems, SpaceX doesn't want us designing right now.
Okay.
So, yeah.
One of the other goals of the competition is a mechanism for public outreach to help spread the word about this developing technology. I would also imagine, once something is developed, you're going to move goods before you're moving people, similar to rockets.
Right.
You blow up a rocket with goods on it. Okay.
A lot of money, but yeah.
It's a lot different with people inside.
Yeah, a little bit. Yeah.
Who's like Hyperloop is war?
So that's a team out in Germany. I think it's Munich
The Technical University of Munich. They've won every single competition so far. The previous competition, they hit about 200 miles an hour, so they added on about 100 miles an hour onto their top speed.
They're expected to hit 400 this year, so.
And in the same distance. That's the other thing is with this competition, you're working within about a 3/4 mile track, so you have to hit the speed really fast and stop really fast.
Yeah, it's not even just about being able to run at a high speed. You have to have the acceleration to get you there fast enough, and also the deceleration to stop you before you hit the end of the tube.
And you can't break SpaceX's stuff.
Yeah, it's expensive stuff.
Yeah.
I was going to ask what gives them such a big advantage, but rather what in general tends to give, I guess, Hyperloop, what are they called?
Teams.
Teams. What tends to give teams an advantage in this competition?
It's going to be the people that work. So there's
They had, 30 full-time graduate students working on this full-time?
Delft has 24 paid graduate
Which is
students.
the second place.
That's their job, that's their research, that's what they're doing for school. There's a team called Swiss Loop, which is funded entirely by the Swiss government because they're the only team in that entire country. So it's really the experience and the funding that really push the.
Some colleges overseas are run much differently than they are here. Over here, this is more of a club, whereas look at top level teams like them, that's their job.
But physically, like what tended to give you guys an advantage over all the teams that didn't get invited to California?
I think it has a lot to do with the design process, making sure that you're as close to being competition ready by the time you get there, before you get there. You go through, throughout the entire year, you do many calls with your SpaceX advisors once you get accepted to the final competition to review your systems, to talk about what you might need to fix, change, that kind of thing. A lot of it is just the ability to adapt and change. Like last year, we had a pneumatic braking system, but we had no pneumatic system actually designed for the pod by the time we got accepted. Sort of an oversight. Also, we were operating at closer to 170 psi, and we talked to our SpaceX advisors, said we didn't necessarily feel comfortable with the system, and they said, throw it out, redesign it. And we redesigned that thing in about how long, Brendan? Yeah. We also redesigned our entire propulsion mechanism last year in about 2 weeks, midway through. Yeah.
They've also been to past competitions, so they have experience of
some of these teams. Yeah.
What the other teams did and what they have to do to get to this.
Like something that we didn't have going into this last competition is they had these safety checklists that you have to go through to get these checklists. Everybody who's been there before had that, but it wasn't publicized before, so we kind of walked into it blind saying, well, we know we have to prove it, but we don't know what we have to prove. So it was kind of scrambling at that point, yeah.
How do you guys test it? Like, you have your own little track that you...
We are working on getting a track built. We're also in the startup phase mostly for this, but I know that Virginia Tech has a track that we are working on potentially going out to use and stuff like that. But we do a lot of benchtop testing, kind of like you guys do, where we say this is a expected situation or something like that. We check the functionality of, say, the brakes. We make sure that they clamp, they don't have any interference, that kind of thing. But a lot of it is you get to test it. You're not going to find a track where you can test it at speed, except for at SpaceX. That's just a...
And VAR does have their own test track. It's not pressurized, but they do have
a full length,
proper length of track.
Mm-hmm. But again, it's a little over 3/4 of a mile, and it's hard to find land for that. Yes.
About how big are these pods?
So last year ours was about 6 feet long, 2 feet high, 2 feet wide. This year we're at I think 10 feet now.
It's 10 feet by 2.5.
Ish. Like, yeah. In the same kind of dimensions.
So you can range. SpaceX says they can be up to 24 feet long. I don't know who's making a pod that big, but there were some ones that were
Massive.
probably about 10 feet long last year.
What do you think, for the people that were on this team, what do you think that carried over from learning that you learned here?
A lot of it. I don't know if you know this, but the vast majority of our mechanical team at Hyperloop at VCU is ex-Blue Cheese alumni. You're looking at the mechanical team and him. So, yeah, almost all of our machining knowledge, all of our sheet metal knowledge, all of our design initiatives that we learned here, we take and we iterate and we say, well, how can we scale this up?
Right, like none of the design knowledge was learned in college. For the most part.
Nope. No, the math is learned in college, but past that.
As an unbiased third party, the people who were on Blue Cheese are probably the strongest people that are on the team. So you guys all came into this with a lot of experience, and so what you guys are learning here, if you're looking to do something like this, is going to apply directly.
These were taken from the what was it?
Unveiling.
The unveiling.
Last year.
Yep.
There's a whole bunch of them, but that's the size. That is the pod. That's
And
the
you can
cover of
zoom
the
in
pod.
there, and you can see a Blue Cheese logo on it.
There's more with the Blue Cheese logo on it.
There you go.
That's awesome.
Yeah.
There's
All the alumni.
and those, the ones on that side are all alum.
They're not at VCU, and they have no association. They just wanted a photo op. Right, Jack?
I have no idea why Cater's even in there.
That's fair.
He came to support.
No, yeah. We appreciate him. Yeah. Yeah, so that's our pod.
Anything else? Thank you very much.